Hello everyone, my name is Jussi Huotari. For the next 10 minutes, let's consider electricity. I'll present a Bayesian data analysis of wind power generation in Finland based on open data. Our lifestyle requires electricity. Electricity powers our smartphones, computers, lighting and so on. But furthermore, electricity usage is constantly increasing. There is an ongoing conversion to electricity in transportation and heating and so on. This is a good trend, because electricity can be clean. Traditionally, we generate electricity by burning fossil fuels. But nowadays, renewable energy sources are not only possible but also profitable. The main issue with renewable energy sources is that they are intermittent. Like if there is no wind, we get no electricity. It's a proper argument, but the thing is that if we can accurately estimate the power generation efficiency, it is possible to minimize the adverse effects of intermittency. So let's take a closer look at wind energy. In Finland, wind generates about 7% of our consumption. The capacity has grown rapidly, and nowadays we get about 6 terawatt-hours per year. Each wind turbine has a theoretical nominal capacity, describing how much the turbine would generate in optimal conditions. In this analysis, I focus on generation efficiency, which is a relative measure of how much out of the nominal capacity we actually get. The literature suggests that generation efficiency is about 1/3. In Finland, using last year's numbers, we can compute that it was 29.5. Our objective is to learn about the trend of the generation efficiency. Is it growing as a result of technological advances? Or is it shrinking because of, for example, the most optimal locations for the wind turbines are already taken? Our second objective is to learn about the long-term patterns. For example, if we predict that at a future time t, the generation efficiency is below average, we can plan to consume less at that particular time. This is called demand response. Like in a small scale, you'd charge your smartphone or car in advance when you know you'll be spending time at your summer house that has no electricity. The first model is a simple Gaussian regression. The second model adds a hierarchical seasonal component to the trend. The dataset is from Fingrid. Fingrid is the transmission system operator, and they provide quite interesting open data about electricity usage and generation in Finland. The data covers almost 6 years, starting from March 2015. Here I have plotted the weekly mean efficiency. As you can see, there is a lot of variance, even though we are speaking about weekly summaries of the originally hourly data. At first glance, the data is just all over the place and it's hard to see any patterns. Can you see a trend there? Maybe it helps if we add a rolling average. There seems to be some hints of periodicality. Let's see. The first model is a linear regression. The main parts are presented here. We fit a normal distribution with an intercept and a slope parameter. The slope will tell if there is a trend. And if yes, is it an upward trend or a downward trend? Here's the result after running Hamiltonian Monte Carlo simulation in Stan. The trend seems to be slightly positive with high probability. The Hamiltonian Monte Carlo diagnostics are good, like you'd expect from such a simple model. The posterior predictive check looks okay as well. The main issue is that we get predictions far in the tails. Generation efficiency should be constrained between 0 and 1. For example, the factual count of negative values is 0. But as we can see, the model has probability mass for negative values. The second model to consider is a time series as a combination of linear trend and a hierarchical seasonal component. The trend, G, is similar to the first model. The seasonal component, S, models the effect of seasons at the monthly level. The idea is that we can learn from the data what is the effect of a month to the average generation efficiency. It's like we have 12 groups, that is one group for each month from January to December. And each of these groups consists of 6 years or 6 observations from which we learn the mean and standard deviation for each month. The hyperparameters theta and tau are the shared mean and standard deviation. I'm using a normal distribution for the combination of G and S again, and therefore the posterior predictive check displays the same issue in the tails as the first model. The hierarchical model is more complex, so it's worthwhile to take a closer look at the diagnostics. Overall, the diagnostics were good, but the histogram of the R-hat values showed more dispersion. Checking in more detail shows that even the highest R-hat values are still below 1.01, so we can be quite sure that the chains have mixed well and converged. The effective sample size is also good enough. Here's the plot of the result. In the figure, each month has a specific efficiency level that causes the curve to step up and down. There is seasonal periodical fluctuation. The monthly variance is relatively high, and the slight upward trend is visible as well. And to me, this looks like we have not 4 seasons, but 3 seasons. The season of relatively high efficiency, spanning multiple months, a kind of middle ground, and one lonely month of distinctly low efficiency. Let's take a closer look at the posterior distributions. There seems to be 5 months that have above average effect, 1 that has well below average effect, and 6 months in between. For comparing these 2 models, I utilized leave one out cross-validation and mean squared error. Both metrics show that the hierarchical model is better. It has slightly smaller squared error and a significantly higher leave one out estimate. The predictive accuracy of the models is not great, or maybe that's wrong. The accuracy is actually okay, but the distribution is so wide that there is little practical relevance. We can say that the generation efficiency for the next 6 weeks is at 90% probability between 0.2 and 0.6. I would say more interesting is the seasonal component. Here again we have the months. July has by far the lowest efficiency. The winter months are more than twice more effective than July. I was surprised to see this big difference between months. So to conclude, wind energy is a feasible renewable energy source. The generated energy varies a lot, even when averaging over longer time spans. Overall, there is a slight upward trend in generation efficiency. During the past 6 years, the efficiency has increased on average 1.4% per year. The energy generation pattern is clear, so that in July the median is less than half of that of the winter months. The full report is available on my homepage. Thanks for your time.